Thanks very much. Okay, great pleasure. Thank you very much.
Okay, thank you.
Thank you, Ilya, for this very kind sharing. And we move to the technical session, as Ilya was saying, with Haijing Li. And her work is the LBM investigation of a reactive electrokinetic flow in porous media towards a phenomenological model. Please, Haijing, the floor is yours. Thank you very much.
Yeah. Yeah, I think I have to do some.
In the bottom right, there is a present now. You should share your entire screen. Try.
Yeah. Yes. Can you see my PowerPoint?
Now, yes, no? Yes, something is uploading. Okay, we see. Please turn it in presentation mode, and you can start, please.
Yeah. So is the first slide there?
Yes, Hello? It is. It's fine. It's the opening.
Yeah. Hello, everyone. I'm Haijing Li from Eindhoven University of Technology. I'm working with Felix Toschi and Herman Clercx. My topic is LBM investigation of a reactive electro-kinetic flow in porous media towards a phenomenological model. The reactive electro-kinetic flow consists of fluids, electric field response samples, and reactions. It occurs in many technical fields today, such as the plasma-involved applications, like the lamps, the medical carrying machines, and the gas-converting industries. So what do we want to study and how? So first, we want to know the interplay between the fluid and the simplified plasma chemistry. The second is we try to get a phenomenological model which can qualitatively predict the result. The work is on a dielectric packet bed reactor. We have positive and negative electrodes on the top and the bottom boundaries. The dielectric packing beads are located, homogeneous located in the reactor. A fluid with only neutral species A will flow into the reactor, and because of the electric field there, electric breakdown reaction will take place. It will make the neutral species A react into the positive B and negative C. And the reaction rate coefficient K of this reaction is a function of the local electric field. From this curve plot, we know that if the electric field lower than this value, the K almost zero. This means almost no reaction take place. We work with lattice Boltzmann method. We have developed a 2D model. We have Navier Stokes equations for the momentum field, the Poisson equation for the electric field, and a quasi-advection diffusion equation for the concentration field. This quasi equation is derived from the advection diffusion equation and the Nernst-Planck equations. In the Poisson equation, this rho E is the volumetric charge density of the charged species. It will include the influence of the charged species in the concentration field into the electric field. And in this quasi equation, this UE is the equivalent velocity that is introduced by the electric field on the charged species. Here are some results. This is the velocity distribution. This is the electric field distribution. And this one is the reaction rate coefficient as function of this electric field. Let's see some details. This is the electric field distribution. And from this plot, we can see the electric field between the beads is enhanced dramatically. And this makes the reaction rate K only exists here. And as the rest area, it is almost zero. This means the reaction almost only takes place between the beads. These are the concentration distributions of the neutral species A, positive B, and negative C. From the plot, we can see the reactant A is less and less because of the reaction, while the B and C will be generated, and the positive B will move to the negative electrode here, but the negative C will move to the other side, the positive side. To measure the conversion efficiency of this reactor, this Q will be the inlet concentration of A minus the outlet concentration flux of A. This is the Q as function of the sphere size, the packing porosity of the reactor, and the pressure drop of the fluid in the reactor. From this plot, we can see there are trade-offs between Q and these control parameters. And the peak point exists. This means the control parameter at this point is most efficient for the reactor. With this lattice Boltzmann model, advances can be made on the control parameters of the reactor to make better use of this kind of reactor. After the lattice Boltzmann model, we tried to get a phenomenological model. In this model, we regard this reactor as a black box. If a fluid with only neutral species A flow into this box, with the phenomenological model, we want to get some information of the outcoming productions. The aim of this model is, without running the test, it can qualitatively predict the dependence of the Q on some control parameters and give advice on the most efficient control parameters at this start point. So let's see, firstly, what's the information we have without running the test. First is the packing geometry of the reactor, including the dimension, the porosity, the bead size. Second is the potential of the electrodes. The third one is the information of the incoming flow, including the concentrations, the velocity, the density, viscosity, and the fluid pressure drop in the reactor. The last one is the reaction that's going to take place in the reactor, and the reaction rate coefficient of it as function of the electric field. These are some derivations based on the information we know. We want to know this lower Q, the consumption rate of the reactant. So we assume the initial concentration of A is Ci. In a unite time, according to the reaction law, the consumed A will be Ci multiply this K. So the left A will be the initial A minus the consumed A. Loop this. At time t, we can see the left A will be read like this, and the consumed A will be the initial A minus the left A. After that, we multiply the average velocity U bar and the cross section of the bed S on both sides of this equation, and assuming the concentration flux like this, we get this Q with this equation. So with this equation, we can know the relationship between the Q and the control parameters of the reactor. This can be the phenomenological model we want. And to get the Q, to calculate the Q with this equation, what we need to know. First one is the inlet concentration flux of the reactant, and inside it, the average velocity of the fluid is required. And the Darcy law will tell us the U bar like this. The second one is this electric field. From previous slides, we know that it is difficult to calculate the electric field for every point. but we assumed it with the average electric field between the beads. Let's see the detail. Here is where the electric fields, the enhanced electric fields are, and we have to further simplify the issue. We have three assumptions. The first one, second one, and the third one. In the assumptions, the blue circle is the real packet beads, and the red square are the assumed beads. The green area is where the electric fields exist. Here are the result. Here are the result of the electric field from all these assumptions and the simulations. From this result, we can see the result of assumption 1 is the most closest one to the simulation. So we apply this assumption 1 to our phenomenological model. The average electric field will be the gradient of the potential drop between the electrodes, and here we only take the green areas into consideration, because from this figure we can see the potential drop inside the sphere is really relatively small. In this equation, this Ny is how many green areas there will be, and in a homogeneously located spheres packet bed, the Ny can be calculated like this. Finally, the average electric field will be read like this, and we add a H into this equation. It is a correction factor to make this assumption 1 closer to the simulation. At last is this T. This T is the time duration the reactant stay in the reactor. And similar to the electric field, we also only take the green areas into consideration. And the T can be calculated like this. This U bar is from the we can get it from the Darcy law. So finally, we have it like this. Now we have every information for this equation. We can use this equation to calculate Q and make some prediction. Here are some results. The blue curves are the results from the phenomenological model, and the purple curves from the simulations. We can see that the tendency of the curves match each other from the simulation and the phenomenological model, and the model successfully catch the peak points for all the test parameters. This is what we want at the beginning. Finally, is the conclusion and outlook. First, we found the dielectric packing beads can locally distort the electric field and make difference on the reaction. And there are trade-offs between the consumption rate of the reactant and the control parameters of the reactor. The third one is the phenomenological model we got can qualitatively predict the dependence of the reactor conversion efficiency on the input parameters. In our future work, we plan to make more simulation tests to verify and further improve our phenomenological model to make it works for more parameters. This is the end of my presentation. Thank you for your attention.
Thank you, Haijing. Thank you very much. Are there any questions from the audience? We have time for one question. Yes, please, Dr. Warnekar.
Hi, thank you for the nice
Very
talk.
welcome.
Can you hear me?
Yes, we hear you.
Yeah, I just had a quick question. You add the velocity u plus ue. Is the second term time varying in the advection diffusion equation?
Yeah. You, yeah, can you see
Sorry?
my PowerPoint?
Yes, I can see your slide.
Are you
Yes.
talking? Can you see my PowerPoint?
Yeah.
Yeah, are you talking about here?
Is the term time varying? Does it vary with time
Sorry,
and
what's your
space? The velocity field, does
sorry,
it
I didn't get
evolve
your
in
question.
time? The ue term, because obviously the u velocity of Navier-Stokes can evolve with time. Is it a function of time? That's all I'm asking.
No, I think no. It is the function of the this UE is let's see, the electric field will have force will make force on the charged species. It will accelerate or slow down the charged species. So this UE is the function of the electric field and the charge the charge of the charged species.
Yes, so if the charge of the species changes, UE will change, right? Is this what I understand?
Yeah.
Okay. So as the reaction proceeds,
with the charge of the.
As the reaction proceeds, you'll get a different UE.
Sorry, my connect not that good. Can you repeat your question?
I think that sorry, but we are running short on our schedule, so maybe you can continue this conversation on the chat, and then you can, if you like, you can meet on the during the coffee break. Okay, I'm sorry, but we have to skip ahead. I'm sorry, Doctor. Okay.
Thank you.
Please, you're very welcome. Sorry for this.
Yes.
Please, we move to the next speaker, Dr. Fan. With the mesoscopic simulations of transport phenomena in reactive systems. Please. Thank you, Haijing, for
hello.
Presentation. Okay, Rongfan. Yes, please.
Yeah, I need to start the sharing.
Yes.
Okay, and now I'm sharing, and yeah, for the slide. Could you see
Yes,
it?
we see it. Yes, please. You have 15 minutes. At 15 minutes, I will ask kindly you to go to the conclusions, and then we leave some floor for the questions. Yeah. Please, the floor is yours. Thank you very much.
Okay, thank you. That's a little bit tight for the time, but I will try to tell everything I know. Okay, so first, hello, good morning to everyone. I'm very glad to be here today to present our work, Mesoscopic Simulation of Transport Phenomena in Reactive System. By the way, I am still a PhD candidate. So my name is Rong Fan. I am from Delft Technology University, the Process and Energy Department. So as you can see from the title, the work is about the simulating reactive system with a mesoscopic method. First, I will give a little bit introduction about it. So the work is mainly about the heterogeneous catalytic reaction. Nowadays, heterogeneous catalytic reactor plays an important role in many fields of industry, like chemical synthesis, fuel producing, and they are used in the upstreaming industry for almost all of our daily use products. The advantage of a heterogeneous catalyst is very obvious, since the catalyst and the reactant is in different phases. So it is simple to separate the catalyst and the reactant, and the catalyst can be recycled. However, this also brings some problems for studying the transport phenomena of this reaction process. Especially the problems involves multiple length scale. For example, the reactor itself can be in the length scale of meters up to 10 meters, but the catalyst pilot inside is much smaller. And the microchannels or the micropores in the catalyst is even in a much smaller length scale. But here is the place where the reaction actually happens. And in this length scale, the finite size effect like Knudsen diffusion stay to play a role. So we would like to actually study those phenomena. However, if you are thinking about the use of traditional CFD techniques, probably need to make a mesh for the reactor, and then you will find out that your grades is much larger for such kind of phenomenon, and it's also much larger than the microchannels and micropores in the catalyst. And if you are using some smaller scale method like typical molecular dynamics simulations, you will find out it would be in a much smaller length scale. The problem itself is a little bit larger for such kind of method. So it is very reasonable to choose the mesoscale method, and SRD came into our mind. Now, SRD as the abbreviation of stochastic rotation dynamics. It is a particle-based lattice-free method, and we think it's with high potential to simulate such kind of reactive system. However, since the method itself has a relatively short history, a lot of aspects is not very well developed. So in this work, we would try to extend SRD with the purpose for simulating a reactive system. So now first I'm going to give some information about the SRD method itself. In SRD, the fluid is represented by cross-grained particles, and the particles initialize with random positions, random velocity. The velocity follows the Maxwell-Boltzmann distribution, which can give these particles a proper thermal fluctuation. And the method mainly contains two parts, streaming steps and the collision steps. In the streaming steps, the positions of the particles are updated by Euler integration with a certain time step. And in the collision step, the system will be partitioned into cubic cells. Within the cells, the relative velocity of the particles relatively to the standard mass velocity will be rotated. A rotation matrix will be used to rotate the velocities with a fixed angle around a randomly chosen axis. So by doing this, we can therefore the momentum of the particles can be exchanged, and the hydrodynamics naturally emerges. So since we are going to study a reactive system, we would especially care about the boundary conditions, because for heterogeneous catalyst, the reaction happens on the solid surface. So in SLD, there are two ways you can achieve no slip boundary condition. First is you can make the particle just directly bounce back with the opposite velocity from the surface, from the solid wall, or you can make the particle bounce back with a new velocity, which still follows the correct velocity distribution. And the second one is called the stochastic bounce back. Later, I will tell again how it is used in our simulation. And I also listed some of the unit and the parameters on the drive of SLD for your information. Okay, so now I have already tell something about the method itself. Then I'm going to give more details about how we simulate the reactive system. So first, we need to define the geometry. To define the geometry for the catalyst pellets or for the microchannels, the micropores in the catalyst. One advantage of SRD is that it is a lattice-free method, so you are relatively freely to define the geometry with any mesh you like. You can define with basic work cells, and with such kind of with it you can even further define like totally random the geometry. And also you That's another way. You don't need to mesh it, but you can also define your geometry based on some shapes which can be mathematically described. Like you can define the catalyst as a spheres, and the spheres can be condensed to be packed in the domain. It will be like the catalyst pilot packed in a packed bed reactor. So after we define the we have the way to define the geometry. We could probably think about the reactive surface. In SLD, you can also simulate a Lamille isotherm reaction mechanism. Like this, when a particle hit on the surface, a type probability test would be taken to decide if the particle is going to stay on the surface, if it's going to be absorbed, or if the particle is going to be bounced back to the fluid. And if the particle is going to stay on the surface, in the next time step, a similar probability test is going to be taken to decide if there is a reaction or if there's a disruption happening to the particle. And therefore, with the probability, the reaction, the rate for the absorption, reaction, disruption can be written out. And now the reactive surface already defined. I'm going to show you a case about how we simulate the reactions in SLD. As can be seen in the graph, so in this domain, there are two surfaces, which one is reactive in the color of red, and another one is not reactive, and enclosed is the SLD fluid. And on the reactive surface, a biomolecular reaction is going to happen. It is then simple, irreversible A plus B to C reaction. And we give it a little interesting feature for this reaction. So the reactive surface will be divided into square grids. And one particle absorbed on one square grid can only interact with its first and second neighbor, and we give it a different interaction between the particles from two different spaces. So therefore, the particle will have a tendency to stay close to the other particles which are from the same species. So with such kind of feature, we will get those particles absorbed and reacted on the surface will form a pattern, which is like an island. So with the island formation, this will lead to a non-mean field behavior, and this will actually influence the reaction rate. We compared the occupation of the unreacted particle on the surface with the mean field assumption and with the island formation effects. And you could see from this graph with the island formation effects that the occupation of unreacted particle will actually increase. It is because that in this condition, the chance that the particle from the species A and the species B contact with each other will be lower. So the reaction rate is also reduced for this reason. And SLD can not only simulate a very simple reaction mechanism, it can also simulate some more complex reaction mechanism. Like this one shown on this slide, it is similar with the cell oxidation mechanism. And the graph of the result, I put it here, it is to show that in the one we are simulating the fraction change on the surface, we are simulating the reactive surface. We can also simulate the mass transfer in the fluid phase as well. So this is what we want for the developing SLD. We would like to have the mass transfer in the continuous phase and the reactive surface reaction simultaneously. So now I have already talked something about the reaction and the mass transfer part for SLD, but we would also care about the energy change during the reaction, because the energy is also energy change will result in some temperature change, and the temperature change will actually influence the rate of reaction. So for SLD, because it is not like CFD, you can directly clearly see the temperature as the parameter in the simulation. But it is a method with some thermal fluctuations. So actually, the only way you can know the temperature is to measure the velocity distribution and to get the temperature from the distribution. Because of this feature, most of the current research with SLD, they actually use the thermostats to control the temperature in a certain range, but not include some real-time temperature change with the reaction. And our ambition is to measure for the chemical reaction, we could measure the real-time and local temperature change. So how we can do that? We have to, like I said, we have to measure the velocity distribution, right? Then we need to collect a lot of samples of the particles to get the distribution, then to get the temperature. The first and the simplest way you can think about is probably is that if you have steady states, then you can measure collect the sample from different time steps and do a time averaging to have the temperature for the whole simulation. Or if unfortunately you don't have steady states, but you have a symmetric system, probably you can still collect the spatial from the different spatial positions to get the average result. But what if you don't have steady state and you don't have the symmetric system, like you want to really measure the temperature in a quite complex geometry and really local temperature? We figure out that there's still one way to do it. If you have many parallel simulations and if they are all equivalent to each other, then you can collect samples from these simulations to get an average result for your temperature. Then you can fit back this temperature to these simulations. So with this, by this way, you can actually simulate the chemical reactions with the real-time temperature change. So now,
please, you should go to the conclusions, please.
Oh, okay. I will just.
Thank you very much.
Yeah, I will just show you some graphs about our case for the. Yeah, we do some tests for the temperature change in the fluid, and also measure the thermal diffusivities, and we also did the temperature change with the between the solid phase and the fluid phase. Okay, so it is a measurement for the temperature change in a solid sphere in the 3D box-like domain with a hot fluid line. So now as the summary for this presentation, I presented 3 development we made for SLD method to achieve the simulating the reactive system. Our future plan is that I hope we can combine all of these 3 development to simulate a realistic chemical reactor. So before and combine and also the transport phenomenon inside it. Before I end this presentation, I would like to thank to everyone who contributed this project, especially master students who did a lot of simulation work. And that's all, and thank you for your listening.
Thank you very much, Rongfan, for this very interesting talk. Are there any questions from the audience? We have time for one question. Okay, if there are no questions, I think that we can thank our speaker one more time. I thank you all for having joined this morning technical session. Now we have a very good coffee break, and then we meet for the last.
Murthy, and this presentation is DSMC investigation of rarefied gas flow in open cavity for all rarefaction regimes. Please, the stage is yours. You have 15 minutes. After that, I will tell you that only 5 minutes are left.
Okay, thank you very much. Hello, everyone. It's nice to be part of this conference and presenting our work. So, thanks for the introduction. I'm from BITS Pilani, Hyderabad campus, India. So, I'll be talking about the rarefied gas flows in an open cavity over different rarefaction regimes. So, a brief outline of the presentation. First, I'll give a background of this problem and the scope of what we are studying, a validation of our case, results, and conclusion. So I think this problem is somewhat different from most of the other talks, which are based on LBM. This is a slight departure, and it's based on DSMC method. So this basically deals with the rarefied gas flows, which are flow of gases at very low densities, and they are characterized by something called Knudsen number, which is defined as mean free path of the molecules divided by the characteristic length scale of the problem. Now, as you see here, we typically deal with the continuum flows where we assume that the medium is continuous, and we do not have to look into the particulate nature of the fluid under consideration. But when we go to the slip flow, which actually different regimes are shown here. When Knudsen number is less than 10 power minus 3, it's continuum, and it between 10 power minus 3 to 0.1, it's slip flow. We can roughly call it that. And then above 0.1 until 10, it is transition flows, and beyond 10, the Knudsen number, when it reaches beyond 10, it is free molecular regime. So this is pictorially depicted in the figure below, where we see in the continuum regime the molecules are closely spaced, and the density decreases as you go to the free molecular regime. So there are several instances where you encounter such flows. Typically the aerospace applications, when we are talking about the flow around satellites or re-entry vehicles or nozzles and jets in space environment. In addition to that, we also see the same flows in micro scale, that is typically in microfluidics. Because as we see, the Knudsen number is given by lambda by L. So in microfluidics, the characteristic length scale is inherently small. So Kn is supposed to be large. So that causes these flows also to be in the rarefied regime. So there are several techniques that are typically used to model such flows. Typically the Navier-Stokes equation failed there because the continuum assumption itself fails there. So for the slip regime, we can modify the Navier-Stokes equation slightly with respect to the boundary conditions and proceed with the modeling. And typically in the rarefied flows, the kinetic theory of gases is employed to analyze them, and the Boltzmann equation is used to model the flow. So if you're talking about the continuum modeling, we have Euler equations at very low Knudsen numbers, and then the Navier-Stokes equation, and then the Burnett equation, which can partly deal with the rarefied regimes. But we also have the particulate methods like DSMC and molecular dynamics, which solve the Boltzmann equation in a stochastic manner. So I think this is a bit of an elaborate chart of comparison of these three methods. So CFD typically uses Navier-Stokes equation, and its computational cost is typically low. And DSMC method solves the Boltzmann equation, and it has a moderately high computational cost, but very affordable for a large class of problems. And then we have molecular dynamics, which solve the Newton's equation of motion, essentially translate the particles, and its computational cost is relatively very high. So in this present method, we employ the DSMC method, where it's called the direct simulation Monte Carlo method, proposed by Professor G.A. Bird, and it solves the Boltzmann equation stochastically. So essentially the idea is, when we have an enclosure with real molecules inside it, we group some of the molecules and call it one DSMC particle or a simulated particle. So essentially the algorithm proceeds this way. We initialize the particles with these DSMC particles with positions and velocities, and move these individual particles as they interact with the boundaries. And we re-index their positions in the entire domain, which is actually divided into different cells for sampling the flow properties. And in each cell, the molecular collisions are performed, which is basically probabilistic in nature. And then the flow properties are sampled as averages of pressures, temperatures, and so on. And once we have the simulation converged, we sample this and output the flow quantities. So in this, that's basically the outline of this, or background of this problem, or the method. So in this present study, we are using the DSMC form solver, which is a part of OpenFOAM, to first validate a benchmark, and then we study the flow over open cavity, where we have three different physical quantities: Mach number, Knudsen number, and the wall temperature ratios, for which we simulated the problem. So first, let me present the validation of this problem over a flat plate. So we have considered hypersonic flow over a flat plate. It's one of the simplest problems to begin with, though, and there are several experimental results by Baker and others for the flow of helium over a plate of 50 mm length and 25 mm width approximately. And the same has also been validated numerically by Habina and the group for these flow configuration or the flow properties. So the temperature is roughly 10 Kelvin and pressure is 0.3 pascals, and the free stream velocity is fairly high, 1700 meter per second, and these are the other flow properties. So here we have a validation of this problem where the solid line is our present study and the blue dots are the experimental results by Becker et al. And the red dots are the numerical results by Hermina. So we have plots for velocity, temperature, and density, non-dimensional quantities, and we see that they agree fairly well with the published results. So please note that these are the Y variation, that is the variation of the flow quantities perpendicular to the flat plate at location 2.5 mm, that is roughly 1/20th of this length of the plate. So somewhat towards the leading edge. So based on this, we have a fairly good validation. So next I'll go to the main theme of this talk, which is rarefied gas flows in open cavity. So again, as we know, this is a well-studied problem and traditional fluid mechanics using the continuous flow solvers. And so essentially we have a flow occurring from the left side to the right side, where the inlet boundary on the left side is modeled as a free stream inlet, and even the top boundary is supposed to be sufficiently far from this cavity, so we also model it as a free stream inlet, though the flow is occurring only parallel to the bottom surface. And the right side surface is modeled as an outlet, and the bottom surface is the no slip wall. However, of course, this is a rarefied flow, and we do see this slip flow close to the wall. And the beginning portion of this domain is given a symmetry boundary condition, so that the flow has time to develop and stabilize. So coming to the computational methodology, well, we are assuming that the DSMC molecules are modeled as hard, elastic, perfectly smooth spheres, and the fluid is taken to be non-reacting air, which is a combination of nitrogen and oxygen for the most part. And for the simulation parameters like time steps, cell size, and the particles per cell, I didn't include it here. We have followed the DSMC guidelines, which typically give the converged results for such chosen parameters. So we have used the solver DSMC form, which is basically a C++ based code under the framework of OpenFOAM. And the collision kinetics to model the intermolecular collision, we have used VHS model, variable hard sphere, with no time counter scheme. So we have varied Mach number, wall temperatures, and Knudsen numbers. So we have used the analogy of a re-entry vehicle at different altitudes, at which we pick the flow properties from the US standard atmospheric tables. And this gives the densities, number densities, and viscosities to the fluid and so on. So based on these mean free paths, we have calculated the Knudsen numbers correspondingly, which are roughly 0.05, 0.1, 1, 10, and 20. So we have studied these cases to summarize in the one slide. So in the first table, we see that the first 4 cases are for constant wall temperature ratio. In other words, the bottom wall where the cavity's surface is, it is held at constant wall temperature ratio, where T infinity is the free stream temperature. And we have varied the Mach number from 5, 10, 25, and 30. And after that, we have held the Mach number to be constant at 25, which is hypersonic regime. And we have varied the wall temperature ratios from 1, 2, 4, and 8. And we have also looked at the effect of rarefaction, that is for different Knudsen numbers, at by holding Mach number and temperature ratio fixed as 25 and 4 respectively. And the Knudsen numbers I have pointed out, they fall in all the different regimes. First is slip regime, and next early transition, next is transition, and on the verge of free molecular regime, and finally in the free molecular regime. So thereby we covered most of the flow regimes. So let me go to the results directly. First is the effect of Mach number. So these are some of the flow contours I would like to show just to get a feel of the problem. Here, as I mentioned, we have fixed Knudsen number to be 1 and wall temperature ratio to be 4. So these contours are only shown for Mach 25, but I'll present the profiles later on for different Mach numbers. So these are the velocity contours. As you see in the symmetry region, the flow is not affected much by the bottom surface, and only when it interacts with the bottom no slip wall, it starts showing strong gradients in the y direction. Well, the cavity is sufficiently far located, and the height of the cavity is 3 mm in this case, and width of the cavity is also 3 mm, and it's located at 60 mm from the inlet, from this inlet surface we have shown. So for a large part, we can see that inside this cavity, we see some recirculation, a big vortex as typically is supposed to be seen. And this is in the transition regime, so it shows a large typical characteristics of flow even in the continuum regime. But we see that just outside the cavity, the flow is very little affected by the presence of cavity itself, as the streamlines from above this point are barely affected by this. And these are the pressure contours, and we see that here the pressure is close to the free stream pressure, and very quickly it goes to very high values just as it encounters the plate, and the pressure ratios are roughly 170, and that is shown by the red curves. And similarly, we also see the temperature ratio, or the temperature itself reaches a very high value. Initially it's much smaller, but very soon it reaches 8000 Kelvin, and so roughly around that. And this is because of a strong shear layer that develops right over the plate, and this propagates downstream and carried downstream by convection. And this strong viscous dissipation, because high shear, is what causes this strong temperatures. And of course, we also have the compressibility effects because the Mach number itself is 25, as we see here. And next, these are the density plots, where we see that again, as the flow encounters the bottom plate, the density shoots up, though the peak is not as sharp as we see for temperatures and pressures. So next, I'll show the contours of the graphs of variation of density, velocities, and so on at these 4 sections. So if this is the cavity, I've taken one section here which is 59 mm, x equal to 59 mm, and this is 61, this is 62, and this is x equal to 64 mm. So at these 4 sections, I would like to show some of the profiles, how they vary over the vertical distance normal to the bottom surface. So these are the 4 sections and velocity, non-dimensional velocity contours profiles at 4 sections for different Mach number. So previous contours are all for Mach number 25, whereas these are for different Mach number. So this 0.06 mm corresponds to the topmost surface of this domain, where flow quantities are barely affected by the presence of cavity or the bottom surface itself. So that's why we see that in all the 4 profiles, as we look at the y equal to 0.06, all the 4 profiles overlap with each other. That is, all the Mach numbers 5, 10, 25, and 30, they show similar values of velocities, pressures, or other physical quantities. Whereas more interesting stuff occurs right at the bottom wall or inside the cavity. And we see that inside the cavity, which corresponds to y equal to 0, we have, of course, a strong vortex. It's hard to see it here. And the velocity profiles themselves take a negative values there.
5 meters.
And this,
5 meters.
okay, sure. And these are the pressure ratios. And we see, like I mentioned before, because of the strong viscous dissipation, we see sudden rise in temperatures and pressures, which show a peak values of 80 to 100 with respect to the free stream pressure. And the same is observed for temperature, because we see the same profiles qualitatively. And in this region with strong shear layer, that's a region of high non-equilibrium where the ideal gas laws do not hold. So their direct simulation Monte Carlo is the only way to predict what's happening. So next we'll go to the effect of wall temperature. And here we see the relatively small effect of the wall temperature. Though obviously near wall region, we see some change in velocities. But for a large part in the velocity profiles, we don't see effect of wall temperature. But we see some effect definitely in the pressures, because as the wall temperature increases, it leads to localized heating, and the pressure and temperature can be expected to increase at those 2 locations. So we see as the temperature of the wall increases, the pressure profiles also shoot up to higher values with respect to the free stream pressure. And same is observed for temperature, though with a relatively less variation. And finally, the effect of Knudsen number. And this will be more interesting, because here we have gone through all the different rarefaction regimes. And if you look at the velocity profile, for example, as we go to towards the higher Knudsen numbers from the black to green curve, we see that the black curves are more steep, sharper gradients, whereas the green curves, we see that they slowly achieve the free stream velocity, and corresponding boundary layer thickness, if you may call, is higher. And that is understandable, because the molecules can diffuse farther when there are lesser number of collisions with the surrounding molecules. And these are the pressure ratios. And we see that again, as the Knudsen number increases, the pressure ratios also increase in the near the wall as well as in the shear layer. And similar trend is observed by the temperature profiles. And we also see a definite temperature jump right near the wall, because as the Knudsen number increases, the rarefaction effects show up as a temperature jump, and therefore we see differing temperatures as Knudsen number increases. So that's basically the results of what we have looked into. So just to conclude, first, the magnitudes of different flow properties increase with Mach number in an overall sense. For example, pressures or temperatures, they shoot up to higher values as we increase the Mach number because of viscous dissipation and compressibility effects. And the increasing wall temperature also results in the same trend, though with a lesser effect. And a significant variation is observed among the flow properties for different Mach numbers, whereas the variation is minimal for different wall temperatures, like I just mentioned. And the velocity profile suggests that at all sections, except inside the cavity, the near wall velocity is non-zero, which is in contrast to the zero velocity at the wall encountered into the continuum regime. So basically, I'm referring to the slip velocity in the rarefaction or rarefied flows, and similarly the temperature jump. And with an increase in Knudsen number, the pressure and temperature ratios increase in the domain owing to viscous dissipation compressibility effects. So these are primarily the findings of our work, and these are the references for this. So thanks for your attention. If you have any questions, I'll be glad to answer.
Thank you. Thank you so much for the interesting presentation. There is time for a really short and rapid question, because the time schedule is pretty sharp. Is there any question from the audience? Okay, if not, let's thank again Dr. Murthy for the interesting presentation, and let's move to the next speaker, which is Vesper, with a presentation titled Simulation of Rarefied Jet Interaction using Direct Simulation Monte Carlo and Kinetic Models. Please, Ellen, the stage is yours.
Yes. Can you see my screen now?
Yeah.
Okay.
Again, 15 minutes, and after that, I will tell you that only 5 minutes are left.
Yes, thank you. Thank you also for organizing this event online. It is very, I appreciate it a lot, and I appreciate that I can talk here about my research. My research is quite similar to the one we just heard by Chandra Murthy. It is again with DSMC. What we are interested in is the interaction between rarefied jets. Where can we find rarefied jets? We can find them in space. In space, we have these microsatellites, and the microsatellites need to propel somehow, and they use small jets to propel through space, and these jets may interact with each other. If we would make a case setup in 2 dimensions, it would look like this. We have here 2 jets. They are accelerated by the vacuum outside in space to the speed of sound at the outlet, and then the particles or molecules or atoms just expand into space. If we look from a continuum simulation at the density field, then we see a very high density at the inlets. We see that in the expansion, the density decreases rapidly, and then we get 2 shocks between the 2 jets because they interact, and after the shocks, the density is high again. Chandra Murthy already told us that DSMC needs to be used if we would like to look at the vacuum flow or high Knudsen number flow. However, if we would use DSMC next here at the inlet or in between the 2 shocks, we have a lot of molecules. That would mean a lot of particles we have to simulate in our simulation, and the computational cost is just too high to do that. And therefore, we would like to use 2 things, DSMC in the outside region and kinetic models which approximate the flow in the high density regions. I wanted to talk a little bit about direct simulation Monte Carlo, but as Chandra Murthy told already a lot, I will just keep it very briefly. We have the Boltzmann equation. We can split it, similar to lattice Boltzmann, into the particle motion and the collision step. The big difference is we don't have a lattice, but we just let move our particles free in space. We can put that in an algorithm where we insert new particles, we move the particles, we let them collide, and afterwards we calculate our macroscopic fields. We have a pairwise collision selection in the collision step, so it is different from lattice Boltzmann. I said before we have free particle velocities, so we can also easily model compressible and supersonic flow. However, the big disadvantage of DSMC is that we need a very small cell size, smaller than 1/3 of the mean free path, a time step smaller than 1/10 of the free mean collisional time. And to have enough collision partners, we need at least 20 particles per cell. So if we do that, if we fulfill all these requirements, we would need billions of particles next to the outlet. And somehow we would like to reduce the number of particles there, and therefore we look into kinetic models. Kinetic models are very similar, or the kinetic models we use are similar to the one in Lattice-Boltzmann. So we substitute our collisions, which we resolve in DSMC, with a relaxation operator. And we have, which means that we, instead of doing the collisions here, we have a relaxation step. And now the big question is, if we relax our current velocity distribution to a target distribution, which target distribution should we choose? And sorry, I forgot these things. Already other people did this, Kumar and Pfeiffer, and they found that if we use relaxation, then our requirements basically half. So we can take double the cell size, we can double our time step. We have to increase the number of particles per cell. If we look at which target distribution to choose, we have a few choices. We can either choose the BGK model, where we just relax our distribution towards a Maxwellian, or we can change the distribution a little bit by transforming the Maxwellian with a tensor, which depends on the pressure, or by shifting it with a vector, which is a heat flux vector. These are two very commonly used models. And last model came up in recent years, which is just to blend these two models, because researchers found that sometimes the ESBGK model and sometimes the Sharkov model is good. And then, of course, the idea comes up to blend the two models to always be able to approximate the flow well. If we look at the properties of these models and we look whether they fulfill the basic requirements for kinetic models, then they fulfill all the conservation and they all relax in equilibrium towards the Maxwellian distribution. The Sharkov and the UBGK model don't fulfill the H theorem, and the BGK model, as we know, does not have a Prandtl number of 2/3, but a Prandtl number of 1, which is why it cannot model correctly the ratio between viscous and thermal transport. If we look at what ESBGK and Sharkov basically do, then we can say that the ESBGK model reduces the stress to obtain the correct Prandtl number, and the Sharkov model increases the heat flux to obtain the correct Prandtl number. After we now know all these properties of the models, let's look at two examples and to compare the performance of the models. First, at shear-driven flow, where we just look at a Couette flow between two isothermal plates at 273 Kelvin at a very high speed of 750 meters per second. We will get viscous dissipation in the center. By that, we get heat generation and a conductive heat flux towards the wall. However, we choose a very high Knudsen number of 0.14, which is between the transition and free molecular regime, and therefore the information exchange between the core of the flow and the walls is not high enough to conduct everything to the wall. Therefore, we get a temperature jump and we will get a velocity slip. If we plot for the models which we implemented in the same solver as Chandramurthy uses, which is DSMC foam, if we compare these models along a line here and plot the temperature profile, then we see first the DSMC temperature in black across the channel. So we have a temperature jump at the wall and an increased temperature in the core. And we see then the BGK in red, and we see the BGK model over predicts the temperature, especially in the center, since it cannot predict the correct Prandtl number. The ESBGK performs much better, but underpredicts the temperature slightly, and the Charkov model predicts the result quite well. If we look again as this plot, but we split it a little bit, we only look now at results from DSMC. We have here our temperature across the channel again, and we can split the temperature into a temperature parallel to the walls and a temperature orthogonal to the walls. We see the one parallel to the walls is very high, the one orthogonal to the walls is not so high, which is of course because of the shear stress which we induce. And if we then look at the deviations between a standard deviation in one direction divided by the mean standard deviation -1, we see that there are some differences which represent basically the differences we see here in the different temperatures. And if we look at the skewness, we see a very high skewness along the whole, over the whole channel. Because of symmetry reasons, it switches, of course, at the channel center. And so we see that also if we look here at one example velocity distribution, that we have a highly skewed flow, and therefore it makes sense, if we think about it, that the Charkov model, which uses the heat flux inside its velocity distribution, performs quite well for these kind of flows. If we now look at thermally driven flows, which is a quite interesting phenomena which we are normally not used to from continuum flow, which is thermal creep flow, which occurs when our temperature gradient is of the same, our temperature gradient along a wall is of the same order as a mean free path. To set up such a flow, we use a case set up by Rarefied, where we have here along the wall varying temperature. At the side walls, we have insulation, and we choose a very high Knudsen number to fulfill this condition of the same order of mean free path and temperature gradient. And because of symmetries, we only have to simulate the 1/4 of the domain, which is, for example, this quarter. And we expect, as I said, a flow from the cold region of the wall towards the hot region of the wall. If we look at the results, we have here first the DSMC plot and the temperature contours. We see here the cold region, here the hot region. The vectors mark our flow, and we have a few temperature contours of the normalized temperature. If we now compare again our three models we looked at, then we see that the BGK over predicts the flow, and therefore the temperature contours are shifted downstream. The ESBGK performs quite well. The Charkov also performs good, but not as well as the ESBGK. Now, from our last considerations regarding the velocity fluctuations, we would expect that now the standard deviations in the different directions are perhaps more important than the skewness, because the ESBGK is able to model the standard deviations, and the Charkov should be able to model quite well the skewness. But if we go along a streamline around our cavity, which is here the streamline in the upper right corner, then we see that the difference in standard deviations, the difference in temperatures is quite small, but we get a very high skewness. So our prediction that that this one should be high is not the case. That if we look at 2 points, which is here first in the hot corner, at our velocity distribution, we see that in the velocity distribution much more is going on than just standard deviation and skewness. We see that especially well if we go now to a point at the top, because here we see that both the standard deviations, the difference in standard deviations and the skewness are quite small. However, our distributions still look quite different because they have a quite high kurtosis, and it seems that the ESBGK model performs well for this kind of flows. After we look now at
5 minutes left.
Okay, thank you. At the performance of the different models, we can summarize, which already Chen et al. Did, that ESBGK is good for thermally driven flows, Charkov is good for shear-driven flows and shocks. And if we go back to our interacting jets, we expect from the continuum simulation this density field, this Mach number field with these streamlines. So it accelerates, and after the shock, the streamlines bend and the flow decelerates. And we expect a high temperature at the inlets and between the shocks. If we look at the non-equilibrium, which we have in this kind of flow, then we have first temperature breakdown at the inlet, which is basically because the particles which leave here at the inlet, they go all after the inlet in different directions because we're in vacuum. And if we look at the velocity distribution along this point, then we see that we have very high velocity fluctuations parallel to the mean velocity and very small ones orthogonal to the mean velocity. And this effect increases the further downstream we go from the inlet. Then another non-equilibrium phenomena we have in this flow is, of course, at the shock. In the shock, we have a small density in temperature before and high density in temperature after the shock, and a high velocity before and small velocity after the shock. And this comes basically down to that we get inside the shock a skewed velocity profile. And also what will happen that the parallel temperature will increase first inside the shock, and afterwards the other energy modes will increase their temperature. If we go along one streamline, here the lower streamline in the upper right picture, then first the temperature will decrease, then our parallel temperature will first increase and the other temperatures will increase later, and after the shock the temperatures relaxes again towards each other. If we now compare our different models, sorry, I forgot that. We have to define where we can use DSMC and where we can use our kinetic models. We do that with a gradient length local Knudsen number. If it is above 0.1, then we have to use DSMC. Otherwise, we can use our kinetic model. If we look at the regions where we can use it, then we can use the kinetic models here in the blue regions, and here in the shock region and the high vacuum region, we have to use DSMC. And here we see these pictures for 3 different Knudsen numbers with increasing rarefaction. If we look at our different models, how they perform, we have at here the density contours of DSMC. In white are the DSMC contours, and brown are the pure BGK contours, and in the lighter brown, we have the hybrid model, and we see that BGK overpredicts the interaction slightly, Sharkov underpredicts it, and ES-BGK predicts it quite well. And that is, besides very small deviations, nearly independent of whether we use the pure ES-BGK or whether we couple it with a hybrid model. If we look at our speed up for these models compared to DSMC, we see that BGK, ES-BGK, and Sharkov need only 1/4 to 1/3 of the time DSMC requires, which is basically due to the fact that we are allowed to use a higher time step size and to use less particles. So my conclusions are that our kinetic models can speed up our simulations in the near equilibrium regions. The rarefied jet we just saw is basically determined by the temperature breakdown, so that we have a higher parallel than an orthogonal temperature, and therefore ES-BGK predicts our interaction quite well. We saw the hybrid kinetic model enhances the performance slightly, but not a lot for the case we looked at. Perhaps it is important for other cases. And then we still have an open general question. Can we somehow define our breakdown parameter based on our velocity distribution so that we choose the correct model? Because we saw that the Sharkov model is good for shear-driven flows and shocks, and the ES-BGK model is good for thermally driven flows and free expansion flows. And the question is, can we decide when to use which model instead of always trying all models and then consider for which case which model is good? Thank you very much for your attention.
Thank you. Thank you so much for the presentation. Is there a really quick question from the audience?
Perhaps I could ask a really quick one, please.
Yes, please.
So when you do your, oh, really nice talk, by the way, but when you do your combined sort of BGK like DSMC, that you need to have an average velocity. So I just wondering how you do the averaging.
You mean an average velocity? So the thing is, we do everything based on particles, and we just define based on our macroscopic properties whether we have a breakdown or not, and all particles have a velocity, and they move all with a velocity, and then they come to the collision step. And in the collision step, I decide either I let particles in the cell collide when I want to use DSMC, or instead, when the density is high, when I am near equilibrium, then I relax the particles. So I still have all, I have the particles with the particle velocities. I take the mean particle velocity and I take the mean particle temperature, and afterwards I just assign a certain number of particles depending on the collision probability. I assign a new particle velocity from my target distribution, and after I did it, I ensure that inside the cell the momentum and the temperature are conserved by rescaling the whole distribution.
Thank you.
Sorry, we do not time. I see that Max Getke did a question in the chat. Probably you can talk via chat because we have to go straight forward with the program. And we have to move towards the third. Thanks again, first of all, Ellen, for the really interesting presentation. And let's move to the last presentation of today made by Robin Trank about the study of the effect of various particle shape parameter on the settling behavior. So please, Robin, you can start sharing your screen whenever you want.
Okay. I think Elin is still presenting.
Yeah, okay, perfect, thanks. Now you should be able to present.
Okay, so hopefully you see my screen now and the presentation.
Yeah.
Okay, so perfect. So I'm going to talk today about a study on the effect, or rather on the influence of particle shape on the settling behavior. And as first, a little video. This is a 2D slice of a particle which has is generated from a CT scan. And you already see that it starts to tumble depending on its shape. It starts to orient itself in the flow, and also the flow velocity depends on a bit on the shape of the particle. So it can be beneficial to understand more of the settling behavior, especially in cases of very fine particles in the region of 100 nanometers to 10 micrometers, where separating different particle sizes can be quite tricky. So first of all, for the simulation, we need to find a way to process the geometries, because what we want to investigate are rather complex geometries, which we might generate from CT scans to investigate the settling behavior of real particles. So first thing we do is we create a voxel representation, which you can see on the bottom right of the screen, and which are generated from CT scans. And we can also, based on this voxel representation, create a smooth transition zone to get rid of the sharp boundary and, so to say, smear the boundary by a Gaussian filter about over 1 to 2 cells. All the other parameters required for the particle simulation can also be calculated from this voxel representation, which is shown here. Namely, it's the area, it's the centroid, it's the center of mass of the particle, it's a moment of inertia, and which can be calculated by the parallel axis theorem. So by this, we generate a stencil, and this will be depicted, as you can see on the bottom left, on the grid which we use for the lattice Boltzmann simulations. So for the simulations, I apply the homogenized lattice Boltzmann method, which is based on the idea of considering the particles as a moving porous media. As you can see in the bottom right, you see the application of the Gaussian filter applied to a particle, and you see the smooth transition zone on the surface. So the blue area would be completely solid, the red area would be fluid in this representation. And if you consider the particle velocity to be 0, you end up with something that is shown here, that you can modify the equilibrium distribution by modifying the velocity you are considering by this factor d, which basically is something like a solid volume fraction. So d equals 0 would mean it is completely solid. In the case of a static porous media, it would be no velocity at this point. In the case of a moving porous media with this particle, it would be the particle velocity, which will be enforced via the equilibrium distribution at this point. So this scheme helps us to simulate and to view these particles on the lattice. But what we need are some forcing schemes, and we also need to calculate the hydrodynamic force that is acting on the particle to calculate its further movement. So we have different forcing schemes at hand. There is, for example, the Shan-Chen forcing scheme, which, as already shown, just modifies the equilibrium velocity. There's also a Kuberstock forcing, which adds a source term to the collision term and leaves the equilibrium velocity unchanged. And also there is a Guo forcing, for example, which changes both of these terms. So in my further presentation, I will compare some of these forcing schemes and also hydrodynamic schemes to find the best one for our homogenized lattice Boltzmann simulations. And for the hydrodynamic calculation of the hydrodynamic forces, there are three schemes considered, which is namely the momentum exchange algorithm, which has been proposed by Lat, and also a modification of it, which has been published by Ben. Also, what is tested is a momentum sink. So what we basically do is that we alter the equilibrium distribution and the collision term by the presence of the particle. So if we consider the change, we bring to the change in momentum, which is basically described in this term, we should get the force. We will see later on that this will lead to strong deviations in a highly dynamic case, probably due to some inertial mass effects, which leads to the point that the hydrodynamic forces are strongly overestimated. However, for the less dynamic or for the static case, the results, of course, coincide and are in good agreement. So let's get to the validation. I considered the case published by Tenkate et al., and which considers spheres settling in the fluid media, and he considers 4 different configurations which differ by the Reynolds number, which is given here. So we have 1.5, 4.1, 11.6, and 32.2 as a Reynolds number. And you can also see the results. The experimental results are depicted by the blue symbols, and some of the calculation results are depicted here with the black and green lines. So what I did for comparison is that I used a high order fit to the experimental data, which had a root mean squared error given up here, which is 0.0159, and compared to my simulation results to this data. So for example, the case where we use a Kuberstock forcing and the momentum exchange algorithm by Venn et al., we get to this root mean squared error of 0.0429, which is pretty close to the mean error of the experimental data. So mean error means in this case that it is the mean over all the 4 cases for the different Reynolds numbers. So for the other results are given in deviation of the root mean squared error compared to the results of Kuberstock and Venn. And we see that some cases like Kuberstock and Lat, or also the combination of Ruhr forcing with the Venn momentum exchange, are very, very close to the configuration given here. But also we see that the momentum sink method proposed earlier gives a strong deviation, which is also depicted in here with the black line. You see that for the less dynamic case with low Reynolds number, it coincides with the green line of Kuberstock and Venn momentum exchange. And you see that the deviation increases with increasing Reynolds number as the hydrodynamic forces are overestimated. Also, there are small deviations, smaller deviations, but still deviations when having a look at a Shan-Chen forcing comparison with Venn et al. Or the Lat momentum exchange. So the best method proved to be a combination of a Kuberstock forcing and Venn momentum exchange. However, some other combinations, especially for this case, are also possible as they give pretty similar results. Then, as a next step, considering the performance of the computations, I investigated the settling of a complex particle in a domain of about 88 million cells. And you can see the speed up depicted in here. And there's also depicted the line for 99.5% parallelizable code, which basically means that the problem scales pretty good on clusters with multi-core systems. However, this problem size with 88 million cells still is pretty small. So if you want to go to a higher number of cores, you will of course need a bigger problem. So to the application and also the statistical evaluation, which is what we are doing it for, we want to investigate the settling of particles. So various shape parameters have to be considered to study the influence of the shape of particles to the settling behavior. So namely, there are, for example, the roundedness, the convexity, or the sphericity, which can describe the various particle shapes, but also volume, aspect ratio, surface, and volume. Also, there have been additional shape factors have been defined in literature to find a new or improved parameter to unify the description of the shape of particles and the influence on the settling behavior. So to the setup, some of the generated particles have also already been depicted in the last slide. They have been generated following publication of Vogelgesang, which is given here below, which basically applies this formula, which exploits spherical coordinates and their symmetry conditions in here by varying and randomizing different parameters, which are given here. So which is basically the distance, the exponent, and for the similarity, for the symmetry condition, some scaling parameters of the spherical coordinates. The setup in which the settling was investigated was that of a box of 70 times 70 times 280 micrometers, and the particle size was up to 10 micrometers. So the size of the box was at least 7 times the particle diameter. Also considered as this size configurations, the particles settle rather slow because they are very small, have very few mass. The case of ultra centrifugation has been considered by applying 80,000 times the Earth acceleration. So 150 particles have been generated and the settling has been investigated. So as a first inspection of the available shape parameters, you can see here a combination of the Pearson correlation coefficient to see how the parameters are correlated among each other. If they are very closely related, it is of course not very sensible to consider both of them, so one suffices. And what we already see here is that we will probably get to a model of 3 parameters, which is namely the aspect ratio, which has a very specific case in here, the sphericity or convexity, which seem to be closely related for the generated particles, and also one parameter of this larger block here in the mid, which is consists of the equivalent diameter, which is of course very closely related to the volume, but also closely related to surface and volume of the convex hull. So what we get from the simulations are a lot of data, of course, and nice pictures. Some of them are printed here. So what you get for some is that you see that there's just the influence of one parameter mainly, or that the parameters are very closely related. For example, this is a plot of equivalent diameter and volume. And each point in this plot represents one particle simulation. So get a closer look on some more interesting plots. We have here plotted the settling duration given by the color, and see that, for example, the Fourier diameter and the convexity both have quite some influence on the settling duration. Also, we see a dependency between the sphericity and also the surface of the particle. So in this case, both parameters are required to describe to develop a proper model of the settling duration. But getting back to the numbers, coefficient of determination has been calculated to evaluate the quality of the models found. And for the medium velocity, we found adjusted coefficient of determination to be 0.9618, which is pretty close to 1, which means that this model pretty much fits the data and the particle setting simulations. The best fitting regressors for this case have been the volume, the aspect ratio, and the convexity. So we have one regressor from each of the previously described blocks, which are rather independent. And so this would be the main finding. And this brings me to the summary. What has been shown is that the particle shape affects the settling behavior. There are quite some parameters which are required to describe, and the interdependence has to be investigated. Also, the lattice-Boltzmann method has been investigated by combining different forcing schemes and momentum exchange schemes for calculating the hydrodynamic force. And by this, it has been shown that the simulation of complex particles is possible, what you also see on the right-hand side of this slide. Also, the performance on parallel systems has been checked. And this brings me to the conclusion. The code is also available in OpenLB, which is an open source that is Boltzmann C++ library. And all the simulations have been carried out with this software. So thank you for attending.
Thank you very much, Robin, for the interesting presentation. There are a short question. We have time for a short question from the audience. Okay, if not, let's thank again all the speakers of this session, and I let the